Yes. Okay. So again, I have to be limited with what help I give, but so if there's any confusion about what has been asked, or yeah, if you look at this question, you're like, I don't know what to do at all. Let's get past that, and then we'll go from there. Or maybe nobody's any questions about that kind. But I just want to make sure that once your additional time begins, you're able to keep going. Yeah. So does anybody have any questions?
About the inner products?
Yeah.
The serial supposed to verify it is it's a valid inner product.
Right.
And the hint given was writing it in a quadratic form.
Right.
I was kind of confused as to how to write it in a quadratic form because I got it in a quadratic form, I wrote that to a quadratic form, but I didn't know what to do from there.
Okay. I guess let's see. I'm gonna try making up an example.
Okay.
Okay. All right. So suppose you have a form like this, where you have something like that. Now, that is not a perfect square. However, you can break it up. Break up a first term. And then this part is a perfect square. X minus 3y quantity squared. So now the thing is, the sum of squares can only be 0 if the individual squares themselves are 0. So you can use this to show that the only time that this can be 0 is if x and y are both 0. Yeah. Okay. So, all right. Okay.
Could you show that something is point-wise convergent?
Yeah.
How much extent you want the answer?
Well, so this really gets to the definition of well, okay, for point-wise, you're assuming t is some fixed value in the interval.
Oh.
So you want to show that for any fixed t, the limit of fn of t equals what it was supposed to converge to. Now, and the thing is, if you find that it does not converge point-wise, then it's definitely not going to converge uniformly. But if it does converge point-wise, it still might converge uniformly. You don't know. Yeah. Uniformly is the trickier one because you actually have to work with the definition of uniform convergence. That's and such that if you have n greater or equal to big N and for any particular t, yeah. So that's what I'm looking to show. Or if you think it's not uniform, the negation of this. Yeah. Okay. All right. I'll just leave it up here. Okay. Other questions? Yes.
About the orthogonal projection,
yeah.
We are assuming that V0 is a subspace of a constant function.
Right.
And we are supposed to show whatever function that is there. But doing this, I felt for V to be for me to be able to show this perfectly, I was thinking if V0 is supposed to be like 1, like.
Well, you can use so it's good. The best thing to do is to use 1 as like a basis for V naught, because it's because the constant function 1, V naught is all multiples of that function. Well, I guess here's what you can do. If you want to show that something is orthogonal to a subspace, it's enough to show that it's orthogonal to a basis for that subspace. So in fact, in this case, you have a one-dimensional subspace. So if it's orthogonal to V naught, it is orthogonal to 1.
I think aside that, even if you choose any constant,
Yeah.
it should still work.
Yes, you can use any constant whatsoever. Yeah, because any constant function is a basis for that space. Any more? Well, I see somebody continuing already, so I will go with that. And I'll get Kristen in here. Oh yeah, I'll make a paper. That's possible. Anywhere. Anyone else? And definitely be very clear about writing your name on every piece of scratch paper, what problem it is. Anyone else? Okay. Yep. I'll have some more up here. Okay, now I'll stop the video.